Okay, we're back. So right now, if you recall, I said on the periodic chart, an atom is in its best form. In that particular best form, you will have a certain number of protons. That's the atomic number. That determines the atom. The number of protons will equal the number of electrons, because as many positives as you will have negative. It's neutral. Then you have the neutron number. Okay. That's in its purest form. I call this deviation from the purest form. In deviation from the purest form, what we're looking at, one deviation is what I'm going to call an isotope. An isotope, iso meaning same, is the same atom, but a difference in the neutron number. Now, with a difference in the neutron number, it will not change the charge, because neutrons have a neutral charge, but it will change the atomic weight. So if you add more neutrons, the atomic weight will go up. Now, as we look at this, so this is what we call the isotope. An isotope is an alteration of the atom's neutron number, and in some, okay. Now, if we look at the neutrons, the more neutrons you place in the atomic nucleus, the trajectory pattern of the neutrons is going to change. Now remember that those neutrons and protons in the nucleus are in a small space, about 10 to the minus 2 picometers. And basically what is happening is they're trying to find an angulation to float around in that tiny space. We in Houston have trouble not having collisions even on Beltway 8 and 610. So thus, when you start adding extra neutrons, then the particles start to bombard. As basically they bombard, they start spitting things out from the nucleus like a collision. But this is what I'm going to call an organization in chaos, because the particles don't just fly out in any size like we would with a car accident. They fly out at certain velocities and certain sizes. Now, because you are throwing away portions of the nucleus, we call it nuclear decay. Nuclear decay. Now, where's the radioactive? The particles coming out are basically what we would call radiation. So, nuclear decay is also a radioactive decay in this particular situation. Right? So, as I alluded to, the neutrons are traveling around in this small space. And as I alluded to, if you add more to that small space, the likelihood of collisions would occur. All right? So, when you add neutrons, as you recall, the atomic mass increases. So we have a carbon 12, carbon 13, carbon 14. My question is, which would be more than likely radioactive? Well, the larger it is, the more chance of collisions, to put it in a loose way. So definitely a carbon 14. Now, remember I mentioned that the particles come out at a certain size and speed. So we start first with the alpha particle, which is pretty much the largest. The alpha particle is basically almost the size of a helium. Helium is quite small. So what will happen basically is the collision would occur and you would throw a particle out pretty much almost the size of a helium particle. Now, we won't get real detailed, but understand this particular particle, since it's somewhat large, its travel velocity is not that great. And basically then it's one of the easier particles to block out. Okay? On the helium, on this alpha particle. Okay? The beta particles are smaller. Beta particles are basically, let's say that a neutron hits another neutron, splits it up, and a piece comes off. The piece comes off the size of a proton plus the size of an electron. So in other words, you got a neutron, you hit it with something, and all of a sudden a piece breaks off the size of a proton, which is not that much smaller than a neutron, and another little piece, which is the electron. So therefore you can see, because these particles are smaller, they can do more damage, because they can travel further, and also they can go through things much easier without getting too fancy. The gamma rays are the most powerful. They actually are just pure energy. They're actually not particulate. So these are the ones that give the most deleterious action. But again, on the radiation, you would have the alpha particles, the beta, and the gamma rays, we'll call them, and this would all fall under the title isotope. Now, be sure to read on this in your textbook also. This right here we'll talk about again, but anything that travels in waves is listed on what we call the electromagnetic spectrum. Here's a wave description right here. Anything that travels in waves is put on this right here. So, in a wave, this is the description of a wave. One is the amplitude, which is the height. The other is the frequency, how fast they travel. And the other is the wavelength, which you see here, lambda. Now, the shorter the wavelength, the faster the frequency. The shorter the wavelength, the faster the frequency. So the shorter the wavelength, the more powerful it is to go through things. I go back to this here. These would be the approximate wavelengths that you have. This going this direction is a smaller wavelength, so more frequency. So therefore, gamma would be very high frequency, then X-rays, then UV. Now right here is what the rods and cones in your eyes can pick up, which we call visible light. Visible light is in that wavelength right there. It starts out with what we call violet, indigo, blue, green, yellow, orange, and red. So a wavelength below red, because remember these are the longer wavelengths, is called infrared, and the wavelength above this violet is called ultraviolet. So this shows relative, and we'll come back to this again when we talk about melanin in the skin and various other things. Okay, we go a little further. Now, the first descriptor I spoke of, you may recall, was an isotope, a deviation in the neutron number. This here is an ion. This is a deviation in the electron number. Okay, with this one, yes, you also could change the atomic mass, but the electrons do not contribute that much to the atomic mass. So the main thing with these are charged particles. These are charged atoms as the result of a difference in the electron number. If you add more electrons, which means you would have a dissimilarity between the number of electrons and number of protons, then it would be a net negative charge. If you take extra electrons away, it would be a net positive charge. So again, this is what we call an ion. Terminology to understand. A negatively charged ion is called an anion. A negatively charged, that's where you would have more electrons than protons. And a positively charged one is called a cation. Because pure deionized and distilled water does not conduct electricity, I'm going to say what causes the conduction of electricity in water are these ions. So since the ions can dissolve in water, we can call them electrolytes, bodies of electricity. Okay. All right. And that is what, like when we get further in ANP2, our sodium in our body is in an ion form, and our chloride and things of this nature there. So an ion is a charged atom as the result of a change in the electron number. Okay. We go next to how the atom is arranged. So we're talking about now electron placement. Now remember, the neutrons and protons are in the nucleus, but the electrons travel around the nucleus. They are placed into something we call energy levels. Some will call it energy shells. Some will call it energy clouds. Okay. There's a certain amount of electrons placed in every level. Certain amount. Okay. So look at your text, but I'm going to say that in the first energy level, which will be the lowest one, the first energy level, you can place a maximum of 2 electrons. In the next energy level, you can place a max, let's say, let's go here. In the next energy level, you can place a max of 8 electrons. And then after that would be pretty much the same thing. So when we look at the periodic chart, we will discuss how these are placed. But the other thing is electrons travel in subgroups called orbitals, and in an orbital a pair. However, I'm not going to get into that. That's beyond the scope for this biology course here. But we go further again. Now, the energy level I mentioned. Okay, so I want you to read in my PowerPoint on energy. Energy basically is the capability to do work. Work in physics is a force times a distance. So since the universe uses conservation of energy, if you gave me an atom and asked me to place the electrons, I would place the electrons in the lowest energy level first. The lowest energy level first. Okay, so the lowest energy level can hold a max of 2 electrons. A max of 2 electrons. I won't get in heavy on energy since I'm not doing this face to face. All right. So here we go with the electron placement in. You place the electrons in the lowest energy level first, conservation. Then you start filling from that. Energy level 1 can hold a max of 2 electrons. Energy level 2 can hold a max of 8 electrons. Okay. Energy level 3 can hold 8 to 18, but we won't get real fancy because when we get into the 8 to 18, then we start getting into higher forms of chemistry. For our practical purposes in this course, we're going to say 2 in the first shell, 2 first energy level, 8 in the second, 8 in the next one, and even 8 in the one after that. Okay? So we're going to make it very simple. Okay? So for example, helium has 2 electrons. Okay? Because you place the first 2 in the lowest energy level, they both are in the first energy level. Carbon has 6 electrons. 2 in the first, 4 in the second. Potassium has 19 electrons. So here we would go. 2 in the first, 8 in the second. That's 10. Right? 2 in the first, 8 in the second. 8 also in the third level, which would leave just 1 in the last energy level. Okay, so we're placing from lowest to highest. Now, another concept of importance. The number of the electrons in the outermost shell is called the valence energy level. So the valence energy level, a valence shell, is the outermost energy level. That's of importance to us. The valence is the outermost shell. Okay. We have something we call valence numbers. We have 2 valence numbers, and some books use one or the other. A positive valence number is how many electrons are in the outermost shell. A negative valence number is how many electrons would need to be added to fill that outer shell. So one is a positive and the other is a negative. And this is going to be of importance to us. Okay. So now as we go further, I get to the periodic chart and look at this electron placement here. But that will be a separate video.